And here we go. We're going to dive straight into 21.2, which is buffer solutions in the human body. To maintain normal bodily function, there are places in the body where certain pHs are required. And in those places, there are control systems that control the pH. And here are some examples of those. Everywhere from the stomach to the small intestines, even your tears have strictly controlled pH levels. The one we're going to look at in detail here is blood. Blood has to stay within a range of 7.35 to 7.45 on the pH scale. Now, if we did 10 to the 7.35, we get 4.46 times 10 to the minus 8 moles per decimeter cubed in terms of the concentration of H+ ions. The difference between 7.35 and 7.45 is about 20%. So it's a 20% difference in the concentration of the H+ ion that your blood is okay with. So what does it do? Well, the functionality of the blood is, of course, to transport oxygen. It's to allow enzyme function and to maintain homeostasis. If the pH goes wrong, then so do these critical systems. So when we say that blood has a pH of about 7.4, we don't necessarily mean all of it, because if you think about it, it's a bit of a composite. About 55% of normal blood is blood plasma. It's the liquid medium in which we find the red and white blood cells. It's vitally important for the function of your body, whereas the hemoglobin on the red blood cells carries the oxygen from the lungs to your cells. It is the plasma that transports the CO2 away from those cells again. And this is going to be really important as we explore the presence of carbon dioxide in your bloodstream. So you might ask yourself, what would happen if the pH became too low, if my blood became acidic? Well, more acidic than usual, we would undergo acidosis, which comes with such great symptoms as fatigue, shortness of breath, shock, or even death. And generally this comes from kidney dysfunction. It can be caused by diabetes, dehydration, or poisoning. Now the opposite of that, if the pH is greater than 7.5, a person can suffer from alkalosis, which is when your blood has become too alkali, with muscle spasms, lightheadedness, and nausea. And it comes from low levels of carbon dioxide being in the blood, caused by hyperventilation, and can be triggered by things like asthma. So your body has to maintain the pH of your blood plasma between 7.35 and 7.45, otherwise there's very serious consequences. So let's have a look now at how it does it. Well, your body does it with buffers. In fact, the particular buffer is carbonic acid hydrocarbonate buffer. And so hydrocarbonate, you can see it on that left-hand side, it has got this double OH on one side and an OH on the other side. And it is this is going to be the acid, it is going to be the dissociation of one of those hydrogens that's going to lead it to donating a hydrogen into your blood at the H+ ion. And the bicarbonate is what's left over, it's the other half, it's the A- in our terminology that we were using. So just where does carbonic acid and hydrocarbonate come from? It's actually a waste product indirectly of the respiration of your cells. Because if you remember from your GCSE biology, respiration was glucose plus oxygen, goes along and gives carbon dioxide and water. Well, carbonic acid comes from carbon dioxide and water in the blood. An enzyme, carbonic anhydrase, actually creates it and releases it as a buffer into the bloodstream. There you go. You literally just add carbon dioxide and water together and we get this H2CO3. Now what we have here is an acid and a conjugate base. Both of these need to be present in the blood so that the blood can resist any changes in its pH level. So here it is. You can see the carbonic acid on the left is in an equilibrium with H+ ions and hydrocarbonate ions. And what you can see here is at the moment, it's a partial dissociation. That's why we're using the equilibrium sign. It's a weak acid, so not all of it is dissociated, and we get them recombining in the opposite direction. So this reaction can go to the left. It can form carbonic acid once more from ions. Now, what happens if we add acid, or if your blood gains more H+ for some reason? Then what it's going to do is it's going to bond with that hydrocarbonate. It is going to be used, it's going to use up the component 2, or the reservoir of alkali in your bloodstream, and producing H2CO3 once more. If you add alkali, it is going to react with the H+ to form water in your bloodstream, which is perfectly acceptable. And so there you can see it. It's a buffer that will keep your blood at exactly the right pH. The way in which this is tested in the exam is to ask for the concentration ratio, the concentration of the hydrocarbonate ion to the concentration of the carbonic acid. And it's this ratio that will indicate other things. It will basically establish things like what the pH of your blood is, but working backwards from the pH and the powers of the dissociation constant, pKa, we can work out what this ratio needs to be for a particular pH. So how are we going to do this? We look at, that's what we're trying to find, the ratio, and we're given two pieces of information, the desired pH and the power of the dissociation constant. Your strategy is going to be, first of all, we're going to write out the formula for the Ka, for the dissociation constant, and then we're going to take those two numbers, the pH, and turn that into the concentration of H+ ions, and we're going to turn the power of the dissociation constant into the dissociation constant similarly, and then we're going to substitute those numbers into our formula for Ka and calculate that ratio. So let's have a look at how we do that. So I think the very first thing we should always do is write down the formula for this occurring. So there we have the carbonic acid is in equilibrium with H+ ions and hydrocarbonate ions. Now, as usual, we can substitute this into the formula that is very similar to the equilibrium constant Kc. In this case, it's Ka, the acid dissociation constant, and what we've got is the products on the numerator line, their concentrations multiplied together, and on the denominator line, we have the reactants. In this case, only one reactant. It is the carbonic acid, the concentration of. And so we've now got an expression for Ka. We want the ratio of hydrocarbonate ions to the carbonic acid. And you can see that both of those concentrations are present in this formula for Ka. We just need to rearrange it. Now, at the moment, we have got that ratio, the hydrocarbonate ion to carbonic acid ratio, being multiplied by H+ concentration. So we need to divide both sides by H+ concentration to get rid of it on that right-hand side. And so doing that, and then we flipped it round, we've got that ratio is equal to the dissociation constant divided by the concentration of H+ ions, two numbers that, in fact, we can calculate. We were given the pH, and so we can calculate the concentration of the H+ ion by substituting into the formula that relates the two. 10 to the minus pH would give the concentration of the H+ ion. 10 to the minus 7.4, it gives 3.98 times 10 to the minus 8 moles per decimeter cubed. That is the concentration of the H+ ion. The second thing we can do is we can calculate the acid dissociation constant, Ka. It's equal to 10 to the minus pKa. So 10 to the minus 6.1, which was given in the question, gives us a value of 7.9 times 10 to the minus 7 moles per decimeter cubed. Now, substituting those two numbers into the previous formula, we know that therefore the ratio of the hydrocarbonate ion to the carbonic acid is Ka over the concentration of the H+ ion, so 7.9 times 10 to the minus 7 divided by 3.98 times 10 to the minus 8 gives a relationship of 20 to 1. So one product of the buffer solution being used up is water, and that entering into the bloodstream is very easily removed by the kidneys. And you can now see why kidney function could create acidosis, because it can't remove the water that the buffers are creating. Now, the other thing that's possibly created in the presence of acid is the carbonic acid itself. The H plus ions bond with the hydrocarbonate ion and it forms carbonic acid. What do we do if we have too much of this? Well, the main removal method is that it's actually reversible. When there's too much carbonic acid, it breaks back down into carbon dioxide and water once more. And so we actually exhale the carbon dioxide. Part of our breath as we exhale has come from the buffers that our blood uses. It is coming from the breakdown of the carbonic acid. It means that faster breathing removes more CO₂, which reduces the amount of CO₂ in the bloodstream. What you can actively do by fast breathing is change your blood pH. I don't recommend that you try this. Now, one little nod to the people that figured this all out. The two scientists, American biochemist Lawrence Joseph Henderson, that's him there at the top, and the Danish physicist and chemist Carl Albert Hasselbalch. These two people, they wrote down the Henderson-Hasselbalch equation. And you can see that what it basically is it looks at that ratio, the ratio of the in the last case, in the last example, it was the hydrocarbonate ion compared to the carbonic acid. So this unspecifically looks at any conjugate base, A minus, and compares it in ratio to the amount of acid that has produced it. And what it does is it basically combines all of the steps that we've just done into one glorious equation, and it basically shows that we can work out the pH of any buffer so long as we know the power of the dissociation constant and those two concentrations. What it shows in some situations is that if the ratio of the base to the acid is 1, that is the case in all strong acids and strong bases, then the resultant pH is equal to the power of the dissociation constant, a result that we found last time